So what we're going to look at now is section 4.2, and this is exponential functions. And first thing we're going to do is define what an exponential function is. So an exponential function, I'm going to kind of just get straight to the point of the definition. I'm not going to write a whole bunch of words. You want to see the exact definition, refer to the book or the ebook. But basically what it's saying is, a definition of an exponential function is let b be greater than 0 and b not equal to 1. Let x be any real number then this form, a function of the form f of x equals b raised to the x power is called an exponential function. So basically you want this b term, or the base, to be greater than 0 and not equal to 1. It needs to be a constant real number greater than 0, not equal to 1. And then x has to be any real number. But here, x is our variable. So that's what makes an exponential function different than what we've been doing in the past. So I'm going to show you some examples of an exponential function and not of an exponential function. So an exponential function is of, let's label it. I'm going to abbreviate and just say expo func. So expo funcs I'm going to do here, and I'll do some not exponential functions. The first one, let's look at something. This one's a pretty common case that we'll see a lot. 3 raised to the x power. You have a constant real number and as your base, which is 3, and it's greater than 0 and it's not equal to 1. And then your variable is your exponent. Next, you can have something like this. Let's call it g of x. 1/3 to the x power. So your x is in the exponent, or your variable is in the exponent. So this tells you that this might be an exponential function. Now you need to look at this base. And is your base greater than 0 and not equal to 1, and is it a constant real number? This is greater than 0 and it's not 1, so it is an exponential function. Let's look at one more. H of x, we'll call it the square root of 2 raised to the x power. Is that an exponential function? Yes. The square root of 2 is greater than 0 and not equal to 1. Alright, some not exponential functions. Let's see if I can fit a couple of them in here. Not expo funcs. Alright, let's call it m of x. And let's say this is equal to x squared. Now this is something we're used to seeing, something that we've dealt with quite a bit, but we need to see if it fits into our exponential function definition. So first you need to look at your base, and is it greater than 0 and not equal to 1? Well, here our base is x, and that's our variable. So it can be any number we want it to be. It could be 0, it could be -10, it could be 1. So that violates our base rule here. Cannot be an exponential function. we can have, we kind of talked about this already by doing that one, but we'll call this one n of x negative 1/3 to the x power. Now the difference here is our exponent is the variable, it's x, so that's fine, but you have to focus on the base. That base is negative 1/3, which is not greater than 0. So that means it's not an exponential function. And then one more, we'll call this one p of x. And 1 raised to the x power. That is not an exponential function because it violates the base rule of it cannot be 1. The reason it can't be 1 is because no matter what x value you plug in here for p, your output is always going to be 1 every single time. So it's just a straight line. And that's not an exponential. What an exponential function looks like. So next, I'm going to show you what an exponential function looks like. I'm not going to get into the exact specifics of how to graph them by hand because you can plug them in your calculator or you can work them out by hand just to save everybody some time watching videos so you can get working on your homework. I'm just going to show you what the functions look like. Okay, now that I have all the boards cleaned off, let's look at just what in general one of these functions will look like. So an exponential function will look something like this. Let's draw an x and y axis. So that's your x, and here is your y axis. So you could have something like this. An exponential function in general will look like this. In this specific case is if your b, the base that we were just looking at, is greater than 1. So this is if b is greater than 1. So you could have, for instance, say f of x equals 2 to the x power or 5 to the x power. It doesn't really matter. Those are just specific examples. This purple graph I drew here is more of just a general what this looks like, and that is supposed to be purple. Sorry if you cannot see it. And this point right here where it crosses the y-axis is a unique point or a special point, and you'll find out when I draw the next graph. So this b greater than 1 exponential graph takes care of the b's that are greater than 1, but there are also other b's we need to take into account, other bases. Remember, the definition of an exponential function was b had to be greater than 0 and not equal to 1. So we took care of all of them greater than 1. Now we have to take care of the ones between 0 and 1. That's where the 1/3 to the x power, it was an exponential function. So we need to take care of those. And it's literally the same graph, but it's reflected across the y-axis for these. All right, and these are if b is between 0 and 1. So you would write it like this: b is between 0 and 1. And just as an example, this isn't something like 1/3 to the x power is what that would look like. So you can graph these yourself and see what they look like. I'm going to leave that to you. That's not a huge deal for me. But it is good to point out some features of these graphs, and some of these features you'll need to know. I say features and I mean properties. So let's say some properties of exponential graphs. And number one we're going to say if b is greater than 1, what type of graph does it look like? What is the graph doing? If you were to read it from left to right, this purple one, from reading it from left to right, or your little man's walking up, it's increasing function. So if your base is greater than 1, you have an increasing function, and that's sometimes called an exponential growth function. So if b is greater than 1, it's increasing, called exponential growth function. And again, I'm abbreviating, and I'm sorry. Expo means exponential. Func, you know what func means. We talked about that in class. All right. So we can make a similar point if if b is between 0 and 1. So 2, if b is between 0 and 1, the function is decreasing. I'm going to abbreviate with decreasing, and it's called an exponential expo decay function. Something else we can look at are the domain and range. So look at either the domain and range are going to be the same for both of these functions. So the domain are all the x values used. So the red graph keeps going to the left to infinity, and on the right side of the graph it keeps going and getting bigger and bigger. So the domain is negative infinity to infinity, or positive infinity, and the range is the same on all of them. I'll go ahead and do a spoiler alert here. There's a horizontal asymptote at y equals 0, so it's never going to touch 0 and then it is only up from there. So the lowest value is 0, and it goes to infinity. So the range is, start with the smallest value, which is 0, and do we include it or not include it? Well, since there's a horizontal asymptote there, that means it's never going to actually touch 0. So we don't include it. And then that goes to infinity. The next one, I just talked about it. The horizontal asymptote HA is y equals 0. And last but not least, they have a unique point. That point is 0, 1. We'll just say shares the point 0, 1. So these are helpful to know. I'm not going to say that you need to sit here and have them all memorized to a T. Maybe what I would suggest is graphing 1 or 2 of these. So graphing 1/3 x and then 3 to the x, and just see the differences. And maybe graph 3 to the x and 5 to the x, and note the differences, what they look like. And then just see how these apply, and just have a general idea in your head of what these look like, because there will be possibly some domain questions, and obviously the horizontal asymptote is important. Okay, so now I want to look at one specific or one special type of exponential function. And first, I'm going to write it, and I want you to think about, is it actually an exponential function? So let's say consider. Consider just means think about, or tell me what you think about this. Consider 1 plus 1 over x to the x power. So is this an exponential function? So you have a variable in the exponent, so it can, as long as it's any real number, we're fine there. Then you also have the variable here. So let's just take a couple cases and see if it's true. If x is 1, that means you plug in 1 here. So 1 divided by 1 is 1. Then 1 plus 1 is 2. 2 raised to the first power is 2. And then if you plug in 2 here for x, then you get 1/2 inside raised to the second power. So what I'm looking at is I'm trying to see, I know the exponent's good, and I'm trying to see if this base, if it will always be greater than 0 and not equal to 1. So what happens with the first two cases, I showed you that was true. What happens if I pick x to be very, very large, let's say, or keep increasing the number of it, so 10, 100, 1,000, 1,000,000, and so on. This portion, this 1 over x, gets smaller and smaller, but we're adding it to 1 every time. So this inside the parentheses will never be 1, so it will never violate our definition of an exponential function, no matter what we pick for x. So this is a unique exponential function, and it produces a unique result that is sometimes, or I guess, I don't know if it's confirmed, that a financial person playing around one day came up with this, but it produces something called the letter E, and it has a value, and E is, let's write it, 1 over x is approximately E, or, well, no, it is equal to E. So it's equal to E, which is approximately 2.78. No, I lied. I knew I was off a little bit. It's 2.718. And it keeps going on forever. So you should do some of your own research about it into the real world applications of E, but E shows up in the real world naturally, and we came across it here by looking at this function, and so I should note here that this only equals E as x increases to infinity. It's not essential that you know how we get to E, but I'm just trying to tie it in, because you're going to see E used a lot for the rest of chapter 4. And so this is where it arises, and you're going to see E here in a minute when we talk about some finance formulas and problems to consider. Alright, so this is still 4.2, and we're going to look at some interest formulas. I need to learn not to write so big, or in proportion, I guess. There are just some details we need to iron out here first. So let's, this is kind of a little definition. P is, let's start over. I know, you hate me when I do that. Just got to get my thoughts here. Suppose P dollars in principal is invested or borrowed. So you can give someone money and you can invest in say Amazon or whoever, or you can borrow money from like a bank to get a home loan. This is kind of where this comes into play here. And at an annual rate R for T years, then we're going to have the formulas I'm going to write on the right side of the board. But first I just want to talk real quick. Suppose Alright, so let's look at example 1, we'll call it. Suppose $5,000 is invested for 10 years and pays 6.5%, 6.5% per year. FDF, find the following. Find the following. So let's look at part A. And let's say I'm not going to go through all the different compounding options, annually, quarterly, monthly, daily, etc. And now that I say this out loud, when I was over here working previously, I said yearly was n equals 365. That should have been daily equals n equals 365. Let's look at part A, and let's say I want to determine the compounded monthly. So what is the total amount in this scenario if it's compounded monthly? So first, let's start by writing our formula and labeling everything that we know. So our formula is A equals P 1 plus R over N raised to the N times T power. And how do I know it's this formula? Well, there's only two to choose from. Remember the first one I showed you, the simple interest? I'm not going to ask you about those. So there's only two of these you need to worry about: compounding n times per year and compounding continuous. If you're compounding continuous, you have that e in there. It's the PERT, the A equals P e to the RT power. If we're compounding n times, which we're compounding monthly here, monthly corresponds to what? How many times per year? 12. So that's what our n will be. And I like to write out everything and then plug it in. You do how you want, but for now let's do it this way. So P is 5,000. R, now R is not 6.5. It's 6.5%, but when you plug in a percentage into the formula, you have to move the decimal over 2 places to get rid of this percentage sign. So you move the decimal over 2 places, and that's where the decimal is now, and you fill it in with a 0. So it's 0.065. That is how you write the interest rate when you're plugging into a formula. So we have PRN is 12, and T we said it's 10 up there. So now we have everything written, and all we have to do is plug in. And this generally is actually the easiest part. What a lot of students will struggle with is plugging this into a calculator. And I'll do my best to walk you through that. If you're having trouble with that, then with plugging a calculator, there are, I'm sure, videos online that can help you how to plug this in easier. So P is 5,000. And then 1 plus is part of the formula, R divided by N. 0.065 divided by N, which is 12. And that's all raised to the N times T power, which is 12 times 10. 12 times 10. I'm not going to do parentheses. There's too many lines up here. 12 times 10. Alright, so to plug this in your calculator, well, you give it a go first and see what you get. Here's the answer, and then I'll write the answer and I'll walk you through how to plug it in. The answer is 9560, $9,560 and 92 cents. Alright, and that makes sense. If you get some outright, think about the answer that you get before you click or you type in your answer into a problem or on the test. Does it make sense to, if you were to get $1 million after 10 years just by giving $5,000 at this interest rate? That doesn't make a lot of sense. So that should hopefully trigger something in your mind. That's a really large number. Maybe I should look at this again. So see if it makes realistic sense. So to plug this in the calculator, what I would do first is you want to do this part first, the 0.065 divided by 12. So do that in your calculator, and you get do 0.065 divided by 12. That gets you some number. And then you want to take that some number and add it to 1. So now you have 1 point blah blah blah, whatever that 1 point number is, 1.0 something. So now you take that 1.0 something it's inside of this parentheses, and you raise it to the 12 times 10 power. 12 times 10 is 120. So you take this 1 point something and you raise it to the 100th and 20th power. Now when you take this 1 point something and raise it to the 120th power, that gives you some number. Whatever that some number is, you multiply it by 5,000. And out should pop your answer. Sometimes this can be a tricky step for students. I'm sorry if you hear my dog walking in the background. She keeps coming in here and bothering me. But try a couple times, try to look up something on YouTube or something to help you plug it in. But the best thing to do is just take it step by step, little steps. Follow your parentheses, exponents, multiplication, division rules. You got to do everything in order. So take everything step by step, write down each individual step if you have to. Alright, so that was A. Let's look at B real quick, and then I want to be done with these. B, we're going to do is compounded continuously. Compounded continuously means we are using which formula? Do you remember? The PERT. A equals P times E raised to the R times T power. And we already have everything known. We already wrote down what everything was. So P is 5,000 times E raised to the R times, E raised to the R, which was 0.065 times T, which is 10. And so same thing here. You're going to have to be careful with how you plug in. And the answer you will get is 957770. So try it yourself if you know where to find the E button. If you don't know where to find the E button, what you would do is you would look on the left side of your calculator if you have a TI-84 Plus. If you don't, then look it up online somewhere. If you look up on here, on the left side of your calculator, you will see an LN button, and that is blurry as can be. There's an LN button right here, and if you look just barely right above it, that you'll see in the background an E to the X power. So you want to click second and then LN, and that will open up E for you with an exponent, and the exponent you type in would be 0.065 times 10, whatever that turns out to be. And so what you want to notice here is that here we compounded n times 12 times here, and we got 9560. Over here we compounded continuously and we got a little bit higher. Now what I didn't show is all the steps. Normally what I would do is I would at least write the answers for compounded annually, biannually, quarterly, and daily, and so on. And the more times that you compound per year, the more money you have or owe at end of the year. So monthly, it's more than annually. If you were compounding daily, so n would be 365, you're compounding more times. Compounding daily would be bigger than this number here, and compounding continuously is the biggest of all.